Good.
Is it time?
Yeah.
Okay. Good afternoon. Thanks for coming. So today we wanted to share the lessons that we learned while implementing the C++ modules feature. This is work that was done by the entire Visual C++ team. And in particular, Cameron took over and fixed all the bugs that I created and added more features that were added during the C++ 20 standardization. I only did the modules TS part. Jonathan cares, who also helped a lot, and then you have the ID. It's the entire team. I can't name all of them. So I'm Gabriel Dusrace. I'm architect on the Visual C++ team and work with the entire team.
And I'm Cameron DeCamera. As Gabby just mentioned, I work on the Visual C++ MSVC front end, specifically on modules.
No, thanks, Cameron. So again, without Cameron, I think we wouldn't have gotten where we are today. So I'm glad to be presenting these lessons with him. What do I want you to take away from this talk? The first is, what were the modules designed for? They were designed to support programming at large. That means, first thing, if you develop your components, he develops another component, I'm the third user who just tries to combine those two to build an applications, then I shouldn't have to worry about the internals of things that we did. Today, that's almost impossible. You always have to worry about header files, leaking stuff, and so forth. The other thing is isolation. Componentization needs isolation, which is that I should be able to understand the semantics of your components in isolation, right? And if those things are done properly, then the theory that I put forward about 6 years ago was that we should get very impressive compile time improvement. And that actually happens to be the case. If you follow some of the lessons that we're sharing here, you'll see at least 10x speed up, 10 times speed up, not 10%, 10x. And the thing that has always bothered me is that in the C++ community, for some reason, we are so accustomed to software that we don't actually understand that we are missing semantics-aware developer tools. If you come from the Java community or the C# community or the Python community, you know that there are a bunch of tools out there that understand your program. Like, you don't always need a C# compiler, you just need to have a representation of the semantics of a program and then build a bunch of stuff from there. Modules are a tooling opportunity, as I said back in 2017, and we're making that a reality. So with modules, I wanted to bring C++ to the 21st century, where we have all these semantics-aware developer tools. So there are various lessons to get from this talk. Some are directed to C++ toolset implementers, and others are directed to C++ users. The first is, as a C++ toolset developer, what can you do to make good on those promises that we made 6 years ago? I'll share some stories here. And knowing that, as a C++ developer, what can you do to take advantage of the fact that the toolset can actually make good on those promises? Those are the things that I want you to take away from this talk. And lastly, I think the one definition rule has become some kind of gospel. And usually when people hear about it, they start shaking because either the compiler is going to do something that will mutate the intended semantics of your program, or they think they might have violated something. Modules actually make it such that you do not have to worry about that. Modules were designed to bring the guarantees of ODR for free. The only thing you need to do is follow proper hygiene code. Like, if you get a choice to do innovation in existing code base, take the opportunity to introduce named modules. Then these ODS guarantees will come for free. So I just mentioned ODR and module. So what are they? When I started, I talked to Biane and said, hey, what is this ODR thing? And he's like, well, when I started in 1979, I talked to Dennis Ritchie, and what Dennis said was, well, it's as if there is exactly one source text for definition of an entity. That was what they had. And then people try to kind of formalize that in the C++ standards specification. Anybody has gone through that knows that it's very opaque. Like that very simple idea has been encrypted in pages of text that says token for token comparison. You have to do name lookup. Template instantiation has to consider this and other context. It's just incredible, and it is not a surprise that people get it wrong so often because the spec itself is just too opaque. And also, I kept complaining, and I was like, Danny, so you gave me an idea that was very simple, one sentence. But this is what I'm getting from the standard. And I was like, well, all those token for token comparison, they're just there to approximate this notion of module system. If we had module system from the beginning, nobody would actually have to worry about ODR. We didn't. We only had header files, right? So what do they bring you? Why do you need to worry about ODR? If you're in a header file world, then the linker has to pick a definition, has to relate the reference to a function or an object to where its definition is. And if you have too many of these things, you're going to get into trouble. But if you make that process very simple, then you just realize that a lot of time spent by linker and a compiler, most of the time parser would bring in a bunch of definitions. We'll produce a lot of them, especially if they are inline functions, which we happen to have, or if they are template instantiations that we put in header files. They get instantiated in a bunch of OBJs. And what the linker does, it works very hard to get rid of all those things that the parser put in. So someone is working very hard to produce a bunch of garbage, and the other guy is working very hard to get rid of those garbage, right? So if you have a system that gives you ODR by definition, guaranteed by definition, you just get rid of all those hard work, unnecessary hard work. So that is why the ODR is very important, central to the design of modules. So modules were the kind of feature. And we have to relate the feature to the past. The past is this thing where we put everything in what I call the global module. It's these unnamed modules where we have to check for ODR as opposed to taking it as a guarantee. And as we know today, the compiler cannot actually, even if it works very hard, it cannot give you a complete check of the ODR. It works hard, but it's incomplete, and the rest just remains on the shoulder of the C++ developer to make sure. And we make mistakes because we're humans. We are human best. We make mistakes. So to make good on the promise of modules and ODR, I introduced the notion of module ownership. So what is this mysterious module ownership? The idea is that every interface or every declaration, every entity that's exported to you, made available to you, the toolset tracks the provenance, right? Where they come from. And this is important so that if the internals of your modules are kept separate so you don't have to worry about clashes, okay? And furthermore, things that are export exposed, they still need to be tracked because sometimes you get clashes in a way that's not intended. For example, the name swap is quite common. Swap in the standard library means exchange two things, two places. But if you write an operating system, the notion of swap is slightly different, right? So If you take those two components that are completely developed independently, and then somehow you link into your program, you really don't want them to be confused. Today they get confused because we do not have precise enough notion. Sorry, today or yesterday, we don't have precise enough notion to distinguish them and to express them formally in the tool set. With modules, we actually have that. And again, modules bring this ODR guarantees. And because now we have the vocabulary to describe those things, the C++ tool sets, they can now track the provenance through the entire thing, from the parser to the linker, and even to the runtime, when do dynamic loading, right? So I'm going to show you, here's an example of situation where you have the notion of weight modules ownership, where compile is not actually doing a great job. So imagine you have two components, M1 and M2, right? On module M1, someone is providing you a library function, libm1, that internally takes dependency on module M1, calls the function f, imagine swap, right, from module M1. And independently, Cameron independently goes on develop component M2, depending on a module M2 that also expose this very useful function called f. When I link the thing in a program main, without actually knowing that libm1 and libm2 independently takes dependencies on functions called f, completely separately. Then try to link them. Most of the time, the linker will yell at me saying, oh, you have a duplicate definition for symbol f, right? And that problem is dumped on the third person who was completely unaware of the internal details of the component libm1 and libm2, right? So today, the language specifications say this is informal diagnosis required. But that's only because we didn't work very hard in the specification to get into an agreement. A better way of actually supporting componentization, which is that you have a compositional semantics of independently developed component, is to have a notion of strong module ownership, which is that when I compose those two things together, the internal details don't matter. They are kept separately. libm1, when I call libm1 function, it uses f from module m1. And the linker is able to trace that back to that library, that module. And the same goes for libm2, whose use of f is traced back to modules m2. The two are never confused. Okay. Traditionally, we have always thought that was impossible. It is not impossible. It is really possible with the realm of the linker technologies that we have today. We don't need to do futuristic research to get that done. This scenario is offered, implemented today by the Visual C++ compiler, and way to get there is not difficult. And one of the things that I hope for the C++ community, the toolset community, is that we all make effort to bring this increased guarantee of ODR to the C++ community, to you who actually use these facilities. And of course, the parser has to do its work, but also the linker has to do its part. So the notion of module as designed in C++20 is not some kind of surface syntactic sugar that is compiled away by the parser. No, it is a semantic notion that permits the entire tool set from the parser to the linker. So the linker has to do its own, it's part of the job to bring this increased safety guarantees to C++ users. Cameron will tell you more about what the parser has done.
All right. Thank you, Gabby. So while Gabby is explaining more of the targets that we were aiming for when we were implementing modules, I'm going to be talking more kind of boots on the ground. What did we actually do in the tool set to support the features and all of the semantics around C++ modules? And in particular, we're going to get to performance. But for now, let's focus on this idea of ODR. So Before C++20, we kind of had the classic ODR check. You know, the standard says you got to compare names in their scopes and their signatures if they're functions. And if there's two definitions of that same function, for example, then you issue an ODR violation. And the compiler front end gets a very narrow view of the program in that respect. It gets one translation unit to get that right. And that's kind of the end of the list. That's all you can do before C++20. By the way, after C++20, the same is still true. This check still applies to anything that comes from the global module, which we'll talk a little bit more about later. So after C++20, things get a little bit more interesting. You can start to import more translation units into a single translation unit. And what this means is that the front end gets a much broader view of the entire program in this respect. So it can start to check ODR in ways that it couldn't do before. So because each of the translation units that are imported into that one translation unit were well formed when they were created, when you import it, it should be well formed in the context of the translation unit that you're creating. So the MSVC compiler implements a persistent translation unit on disk in terms of the IFC format, which is an abstract semantics graph. And this is our module BMI for anybody who's familiar with that terminology. And if you're more interested in the makeup of that and what we mean by semantics graph, definitely take a look at Gabby's talk on Tuesday, where he talks about persistent in-memory representations of C++. So what can we do now that we have graphs stored on disk and we have a conceptual graph for the current translation unit? Generally, C++ is modeled as a graph. So the easiest way to check for ODR, because we have two graphs, is we can do an intersection. And if you have a set of declarations A and a set of declarations B, you take the intersection of those two, and if that comes up empty, you have no ODR violations. Otherwise, if it comes up with something in it, then all of those entities are conflicting in ODR in some way. So the front end can sort of do this, and you don't even really need a compiler to do this because the IFC is a graph on disk. You could take some third-party application and check for ODR amongst all your IFCs on disk. You don't even have to compile your code anymore. So that's enough about ODR. Let's talk about ODR again, but in the linker side this time. Before C++20, the linker had a very easy job when entities were defined in the translation unit and they were TU local, which is something the standard defines as something that could be static or something that essentially a name that does not escape the current translation unit. And the job is very simple. If that is not defined, it issues a unresolved external reference. I'm sure everybody's run into this at some point. And the job gets a little bit harder when you talk about external linkage entities. External linkage symbols. What the linker will do in this case is it creates this giant map which contains all of the names of the entities as a key, and the value will be where its definition is. So it's trying to map references of a name to some definition wherever it may exist. And this is what I define as the great hunt. So when a name is encountered, it has to go and try to find it in this giant map. Conceptually, the pipeline looks sort of similar to this. So we have a function f, goes into the front end, goes into the back end in a very linear fashion. The back end emits just a mangled name, and that mangled name has an association that says, hey, an external linkage symbol. That's all it needs to know. And it just goes directly to linker, and that's all you have. Down below, you have an example of what the linker map might look like. It's just name, where's the definition? Some definitions might not exist in the case of B, in which case you might see a linker spew that looks like this. And who loves seeing this on when you're building your application, right? So like, how do you even begin to figure out what went wrong in this case? Like, where do you even look for where the definition might have been? And the answer is it's never obvious. It almost never is. So in C++20 and under strong ownership in particular, we could do a lot better. So strong ownership in the MSVC toolset introduces a little bit of extra bookkeeping into the linker. And by this, we mean that it sort of keeps track of when a module is built, what names is that module exporting, and it associates those names with the name of the actual module. So it kind of creates its own isolated component, as Gabby mentioned, and this becomes its own universe of external linkage symbols. This is an example of what that pipeline looks like. So we have similar situation. We export void f. This is an external linkage function. Goes into the front end, but this time the front end will convey some ownership information about f. In this case, it'll say, hey, this f belongs to module m, and it's external linkage. And the back end will retain that information and record it into the object file. And when the linker reads that object file back, it gets not only the mangled name, but the ownership information about that name. And this is what contributes to these maps down below. Now we have, let's say we have two other modules, M1 and M2, and then we have the global module, which is conceptually the old giant map that we used to have. And these are kind of their own buckets of associated definitions between names. So you can even see that there is an overlap between these names. For example, A here is an A.obj, and A here in M2 is an M2.obj. And the linker is totally happy with this because they live in their own isolated buckets of external linkage symbols. Totally fine. And so now you can get diagnostics that look sort of like this. We know that the diagnostics can be improved in this case, but it gives you some indication of where the definition of this function f might have been. The first function there is void g, so this belonged to the global module. That's the same mangled name that we're all used to, whereas f has this extra association, says, hey, you know, I belong to m, which is that not m. It's not really a mangled name. That is just something that we appended onto the diagnostic message. But you kind of get an idea of where to look for the definition of that function.
Yeah,
Over to Gabby.
Before going to performance, just wanted to add that, so that module M ownership, the mangling part is actually something that is done by the linker, not by the front end. Because if the front end has done it, then we have been already too early and the linker wouldn't have found what they need to find. Okay. That being said, you can see the division of labor. The parser does something, associate information to where things are coming from. And then the linker gets to pick the pieces from there. And when it's looking for information where these symbols come from, it starts from, oh, which module, right? And that dramatically narrows down where to search. And you can start imagining where the performance can come from. Well, the things what you have to remember is that in the, what I call the old days of hash includes is just copy and paste of a source file. The motto of C++, you don't pay for what you don't use, is actually violated big time. Imagine you have the simple program, hello world, you include hash iostream, and then you just say, cout hello world. Well, it turns out in iostream, there are a bunch of stuff there that we don't actually use in the body of the main. Yet, because it is copy and paste, a parser and the semantic analysis have to go and pass all those things. All the other template stuff gets to be instantiated, even if you don't use them. Right. So in the old world of hash include, now textual inclusion, you actually do pay for a lot of things that you do not use. Modules fix that. Okay. The other thing is that if for some reason you find yourself in a situation where you can't use named module, I really want you to use named module. That's where you get the real stuff from. Well, you can use header units. Header units are some kind of fancy names for PCHs, precompiled headers. They give you some benefits of modules, not real stuff again. But when you do actually use name module, you get spectacular compile time improvement. So in numbers that we'll show you later, especially Cameron will talk about that, from the current state of the MSVC compiler, we haven't had the 25 or 30 years of experience optimizing PCHs, right? We've just focused on just implementing the basic functionalities. We'll work on improvement, on optimizing use cases. But what you just have with just the basic implementation is already very, very promising. So here, Cameron will walk you through the example of performance here.
Thank you, Gabby. So as Gabby alluded to, hash include has some overhead. Let's figure out how much overhead that actually is. These numbers were taken from Bjarne's paper, integrating a minimal support for standard library as a module. In particular, these numbers were gathered with Visual Studio 16.11. So all of the optimizations that we're going to talk about throughout this talk are part of that release. So let's focus in on what we're trying to measure here. And it's this green square down here, which is int main std_cout hello world, the canonical C++ hello world program. Everybody has probably written this at some point. So let's focus on the first comparison that kind of logically makes sense, which is hash include to header import. And as Gabby mentioned, these header units are really kind of just a formalized PCH. So they store some stuff in there. In particular, they store things like macros, and we'll talk about why that's an overhead later. But here's kind of like a valid comparison between these two things. They should ideally have the same exact contents. So when you switch to header units, you get a 5x speedup, 5.13 speedup. That's already pretty good. But when you compare the hash include, and when we say needed headers here, we're just talking about IOStream, hash include IOStream, because that's really all you need for std_cout. You get a 17.55x performance speedup. And this number is really great, but it's even worse than you might think. And because the reason for that is because when we said import std, you don't just get IO streams, you get the entire standard library. So we're not even close to comparing apples to apples. If we wanted to get closer to that, we have to look a little bit harder. And in particular, we have to do some comparisons, which honestly, the numbers here speak for themselves. So if we do hash include all of std, which is hash include of every single standard library header, which would mimic the contents of import std, you get a 66.51 speedup. So forget about hash include. Like that's just totally gone. But when you talk about the comparison between name modules and header units, you would think that the comparison should be pretty similar. But it turns out that's not the case. You actually get a 7.11 speedup just using name modules over import std. And there's a couple of reasons for this. Header units have overhead. And I mentioned this before, but header units, after you say import like IOStream semicolon, what the compiler has to do is it has to also import all of the macros immediately after that semicolon is done. And this is non-trivial work. It has to create macro objects, paste all the text from the IFC into that macro. So there's a lot of overhead just materializing all of the macros from the IFC. On top of this, headers have include guards, which are not just if def header.h. Usually they come in the form of pragma once. And pragma once has a special implementation depending on what compiler you're in. So the import mechanism for importing that header include guard might have additional overhead on top of the macro that it could import for a header unit or for a header include guard. And finally, importing declarations from a header unit does something that modules don't have to do. And this is merging declarations with any existing declaration that's already in the translation unit, because stuff like this has to work. So if I have some header that said hash include vector, so this is the copy and paste textual inclusion of header, and then later on another header said I want to import vector, and finally in my translation unit I say, hey, I want to instantiate std vector, there is some things that need to happen in the front end to make that work. The compiler must provably say that, hey, this std vector that you're instantiating is the very same one that was textually included in hash include vector. So the module machinery has to say, based on the structure of the class, match it for OER, and not only just the class, but you have to match all of its base classes. You have to match all of the special member functions, all of the default arguments. So there's a lot of overhead that's involved with mixing hash include with import, and really all of the overhead is specifically centered around the fact that we chose to use import header units. So let's try to focus on named modules in general, because they give us a lot better perf. The ODR, when we're talking about ODR with name modules, the comparison is very simple. If you have that name in your translation unit, you immediately issue an ODR violation. You don't have to do any comparisons or try to merge declarations. You don't have to do any of that with name modules. And that's a lot of what contributes to the speed win from header units to name modules. So how do we achieve performance in the compiler front end? And we're going to dive a little bit into some code sample that I got back in 2018. Kenny Kerr, the author of the C++ WinRT, came up to me and said, hey, modules perf isn't where it should be. We should be able to do a lot better. We should be competitive with PCH. And reluctantly, I agreed. And much to my dismay, I had to implement a lot of really painful optimizations around this. So he gave me this code sample. And in this sample, it's very simple. All it does is it reads an RSS feed and co-waits on the result of that RSS feed and prints it all out. Pretty simple application. And this is kind of the graph we ended up with for performance. So the scale on the left-hand side here is in is in seconds, and the X is like commits that went into MSVC. So lower is better in this case. And I implemented 4 optimizations, which took us from about 6 seconds of import time to about 1.8. And the first one of those things is delay loading. So delay loading, it's a pretty simple concept. And the idea is that when you import a module, what it should conceptually do is just populate names in scopes. You don't have to materialize anything, because all of the semantics of name lookup should result in materialization later. And what I'm referring to when I talk about materialization in this case, I mean the process the compiler takes, which reads the semantic information from disk and creates a symbolic entity in the compiler, which it can use to generate code with later. So name population. This module on the left-hand side has a couple of Fs in various scopes, and it kind of translates to a graph on the right-hand side here with these buckets. So we have the global scope at the top, and inside that global scope we have void F, and we have a bucket named N, which is a namespace, and inside that bucket we have another void F, and so on and so forth. So like I said, name lookup drives materialization. So when you say import M here, the compiler is going to say, okay, when you do a lookup of N::F, it's really going to become a select over the graph. So when that happens, all we really have to do is retrieve the entry void F and take all of its semantic information, materialize it from the IFC, create a symbol for it, and off you go. This is what we refer to as on-demand materialization. Template specializations. So in the context of delay loading, let's switch gears a little bit and talk about template specialization, because that demand loading optimization has actually been in the compiler since the TS era. This particular optimization is one we implemented for the C++ WinRT. And every compiler is going to have some kind of representation which is similar to this for templates. So when you create a template, it's going to create this map of specialization arguments to what type of specialization it is. In this case, we have a whole bunch of explicit specializations, and then we have an implicit instantiation. So for correctness, the compiler kind of has to know when a template is ODR used, so it can figure out whether you're using an explicit specialization or it needs to actually instantiate the primary template. And the compiler's already really good at this. So if we take advantage of that and apply an optimization over that, all we really have to do is say, you know, instead of materializing all the explicit specializations, we're going to go ahead and just reserve all of those slots and say, hey, you know, come back later. We'll resolve this thing when this is actually ODR used. This is kind of the map that it creates right here. And on the import side, we have import M, and when the user says, hey, I want to specialize S of char, it says, oh, okay, I have that template specialization. It's a delay load specialization, so I actually need to ask the modules code to go ahead and materialize this thing for me. So you give it the ID of that specialization type, and it comes back with a symbol. And that's how we get this resolved explicit specialization here. And the other ones are just still reserved. We haven't done anything to them yet. And of course, implicit instantiations are the same as they had been before. So it's worthy to note that this optimization relied on a data structure that was that was defined by Sean Parent in CppCon 2019. And it turned out that that data structure, when I saw it, it was the exact right application, or this was the exact right application for that data structure. So go to CppCon, you learn stuff. And that gets us here. So our first optimization. Using right data structures. So when we were benchmarking the modules code, we found out that we were using a lot of std maps all over the place. And it turns out that std map, when it allocates keys, they're not very close to each other. So when you need to iterate a whole bunch of keys, that results in a pretty large perf overhead. You know, what if we try to use something different? So like, what if we try to use bucketed hash tables? And it turns out that gave us just enough of a perf win to justify switching all of them to bucketed hash tables. And it wasn't just on this repro that you were getting the benefit. It was across the board. All the modules repros we tried after switching to bucketed hashes gained at least some perf increase. Serialization technique. So the IFC is memory mapped in the compiler for faster random access, because when we're materializing semantic information, that information is kind of spread across the file at various points. So you have to be able to bounce around the file very quickly, and memory mapping is a perfect application for that kind of thing. It was initially thought that when we implemented the IFC, we needed to kind of validate the contents, that they haven't been doctored in some way. So what we did when we exported an IFC is that we summed up the contents, we created a hash of that, stored the hash in the IFC, and it's still there today. But then on import, what the compiler would do is it would first read that hash and then read through the bytes of the file and say, hey, I need to create a hash of all this stuff and compare it to the one that's stored on the IFC. Just kind of as a very quick validation that nothing's been tampered with. What if we turn that off? So that's a pretty big perf win, and here's the reason why. The overhead was not in computing the hash. Completely negligible in the context of this overhead. The real overhead was the fact that we had to page in the entire IFC, sum up the bytes, in order to sum up the bytes. So we went over to our friends at the C# team to figure out, because they had something similar a while back where they'd validate some kind of some kind of hash that was stored on assemblies, and we said, hey, what did you do for this? They opted to also ditch this ditch this strategy because of perf overhead, exactly for the same reason, in favor of trusting the application itself. And we decided to do the same thing, but we're still providing a mechanism in the compiler to check that IFC on import. So if you're still concerned about the IFC being doctored, you can throw this switch, and you get kind of just a first level validation that nothing's been changed in the IFC in some harmful way. So we recommend at least trying to check that hash at some point, even if you do it through a third-party tool, because it doesn't have to be the front end that checks it. Right, so this is kind of the mantra of every performance benchmark, or anybody who's working on performance in an application. You got to measure everything all the time. And after we measured one last time, we found that it was partial specializations this time. The previous optimization I talked about was only applied to explicit specializations because that mapping was obvious. But partial specializations are a little bit different. Because they don't quite map to an exact argument. And in fact, the way they're modeled in most compilers is that they'll have a map themselves of non-dependent specializations of that template, that partial specialization, which are instantiated. So they're a little bit more complex, but it was actually worth it to delay load them. And that got us to our 1.8 speed up.
Okay, thanks, Kevin, for the detailed explanation of the journey going from the not very competitive implementation I had and where you took us to. It was a very instructive learning for myself. We had a long conversation about what needed to be done, and he was very perseverant and get us there. Okay, so most of what we have talked about so far is about the traditional tool sets, command line stuff like parser, code chain, and linker. But these days when we work in some kind of integrated environment, have an IDE experience. There are several IDEs out there. If you're also into cross-platform development, then you actually have not just one compiler, but several compilers in your environment, right? And in general, people expect some kind of consistent experience across the platform. So you easily see that in the IDE, you're going to have several compilers trying to understand the same code base. So what happens in that case? Well, if each compiler has its own format for storing all these metadata that is needed for modules, you can imagine that you get into kind of real mess. And you may not even get the increased performance that we were talking about earlier. So if you're developing an IDE, if you want to bring this performance that we have proof for that, we can have it today, then it makes sense to actually share that common representation across all the compilers, or at least have all the compilers the ability to emit this common binary representation. Tomorrow I'm going to talk a little bit more about ideas about how to get there, and my expectation, my hope is that in the coming months or years, the C++ community get together to define a common representation for these artifacts that you get from compiling modules. And it will be a sea-changing event for the C++ community. So if you just have all the compilers agree on one format, then you get really good benefits, good experience in the IDE. It's very snappy. The other thing is that in the old world where we have header files, people have systematically complained about header files taking a lot of time. So compiler writers have developed this notion of PCHs. They tend to be this kind of section of code where say hash include, and a compiler, okay, just load those things, process them, and then save the result on disk. So what does that mean, saving the result on this? For some compilers, it means just dump the state of the process right now, and the next time someone is, just load back the process. That'll go very fast because the operating system knows how to load those things very fast. It works. The downside is that what the compiler says on this is the state of the process at that time with all the other stuff that's going around. So you can't move them around. You cannot share them with other projects. If you have used vectors many times across different projects, you cannot share the PCHs across the project because each project has its own memory state when the compiler generates save the PCH. For some other compilers, oh yeah, I'm going to save on this some structured data, right? And that can be some kind of performance. But if you want the ability to share across translation, across project, then you need a common representation. I guess what I'm trying to say here is that the same kind of increased performance that you have with the batch compiler, the one that generates code, you can also bring that performance benefit to the IDE if you get all the compiler writers to agree on some kind of common abstract representation. You C++ developers, you deserve that. You should talk to your compiler vendors, and that includes MSVC folks. Just go on their website and keep asking till they deliver. And don't tell my employer that I told you that. The other thing is that when you're in the IDE and you're just writing import std, like Diana's example earlier, or someone hasn't, for example, built a module, let's say Qt, have import Qt in the brackets. Behind that, the IntelliSense engine needs to systematically compute the dependencies, right? You don't want to be maintaining the dependencies by hand. Nobody wants to do that. So the IDE, the development environment, needs a way of computing those dependencies systematically for you. We go back to the same problem that we had earlier with the representation of the semantics of C++. For the dependencies, it wouldn't make much sense that each compiler or build system has its own way of representing dependencies. You want to be able to share those information because it is the same program. It doesn't matter which compiler you use. Your program is your program. It has the same dependencies no matter what compiler you use. So one thing that I hope that we're going to get is a shared format to represent dependencies of C++ programs. And thankfully, the Kitware folks have put forward a schema that all tool vendors are encouraged to use to report dependencies. The MSVC compiler has implemented that format. And the specification of that format will be part of the upcoming modules tooling technical specification. So WG21 has been busy. There is a study group that was created to help move forward the tooling ecosystem, especially because we got modules that kind of challenge the traditional header file. So the upcoming technical specification for the modules tooling will recommend this format, and we expect that tool vendors would get involved, and most of them are already part of the conversation going on. So the IDE needs to do its part, and so this is mostly advice to tool vendors. But what you as C++ programmers should do, get away from some of the old habits that we learned in the past few decades.
Yeah. So I don't know about you, Gabby. Do you feel like using PCHs anymore? Yeah. Okay. So don't use PCHs anymore. We have a better tool, and it's standardized now. In particular, you should start with name modules, and you should practice them and use them frequently if you can. Because the opportunity to improve your project's hygiene vastly outweighs any possible benefits that you could get from using PCH. For one, they could be reused across projects because it's a portable format that we have designed ourselves. You can move it from machine to machine and it'll just work, unlike PCHs. And oftentimes you'll see that it provides initialization guarantees that PCHs may not be able to clearly define. And this is actually defined in the standard itself. Finally, PCHs in MSVC are notoriously large because it is just a memory dump of the compiler state, which is then memory mapped back in. So you'll see PCHs which grow, up to 2.5 gigabytes sometimes, and sometimes you can't even remap them back in because they're so big. And that's like a huge problem. IFCs are generally magnitudes smaller than that. We've seen 2.5 gigabyte PCHs translate to 600 megabyte or less IFCs. And if you're really stuck on header files, and if you're in a hurry, you can try header units. You get some of the benefits of name modules, but not all of them. Our recommendation for sure is to start with name modules if you can.
Okay, so this has been a very long journey. For me, it has been, 6 years? It's 4?
4 years?
Yeah, 4 years. So we learned a few lessons in the way. When I started, the MSVC compiler would use what I would call ancient technologies to process template definitions. So, and it wasn't actually the only compiler. There were a couple of other commercial compilers out there. So what they will do is that when you write template definitions, they will store the template definition as sequence of tokens. And this is really, really good. It goes very fast. And when you want to specialize a template like vector of int, what they will do is that they will just replay the token streams and then set up scope whatever it needs, like say T there, and there's now int, and then reprocess everything. So you run a parser every time you want to specialize a template. Please don't do that. If you're an implementer out there doing that, please consider moving to graph-based semantics. Parsing C++ code is a non-trivial amount of, it takes a non-trivial amount of time. And in the case of MSVC, if you're still using Yak, it's not a good place to be. So we decided to move a little bit away from Yak processing tokens for templates definitions to, instead of storing tokens, we're going to store the syntactic grammatical construct that we use there and then re-instance it from there. That experiment took about 6 months. I'm like, no, don't do that. There are still, not just MSVC, there were a couple of other compilers they're doing that. Please do not abandon tokens, abandon parse-trees, because you will not bring the speeds that you can actually, programmers can have. And one last thing that was quite interesting is that usually, every time we have new C++ standard, we don't erase the previous one. We only add or improve. So the existing compilers, they already have their framework. And sometimes they insist, like, this is how we used to do things, then you should do it that way. With implementing modules, what we found is we need flexibility. We need to be able to be flexible. For MSVC, for example, how simple things like how do you specify options doesn't actually work very well, because you have to say something like, construct a unit, have to use colon to map command line to argument it will take. But again, that on Windows, for example, colon can also be used to delimit driver from file path. And when you're using modules, you need the ability to map a module name to where the compiler can find its metadata. And if you have a bunch of colon in there, it doesn't work. So we have to go back, talk to the architects, say, hey, and I understand why it was done this way, but I think we need to do something else. Another lessons that we learn, especially with strong ownership, modules ownership, is we need to do something with the linker. So usually when you say we need to do something with the linker, everybody is like, what are you talking about? Like, no, we need to do something with the linker. Okay, so we had to sit down, talk a lot, and convince the linker people, because linker people, they are very close to the operating system. They're like, oh, we need to add a few more information. I need to do a little bit more work. Are you okay? And I guess I can make it work. And they went away. I thought it would take a week, and they came back 24 hours later. Oh, it's done. And we get spectacular improvements. And we have increased ODR guarantees, as we showed earlier. So it pays off to actually be flexible and listen to feedback, consider new ideas. And I think that the C++ tool provider authors can actually do that for the benefits of the larger 5 million plus C++ programmers. I think this is probably we're ready to take questions. But before that, I just wanted to briefly mention that there are some other talks by Microsoft folks tomorrow. I'm going to talk about how to represent C++ programs in memory and on disk, prompted by modules implementation. Sonny there is going to talk about static analysis, how you can check, doing checking modules and static analysis. Herb is going to offer some thoughts on pattern matching, and Sai will talk about what are the opportunities for better error message with concepts that we have now in C++20. With that said, the floor is open for questions. Yeah, okay.
I think back there.
Yeah. Okay. Could you use the mic? Oh, is there a mic? No,
There is
okay.
no
You
mic.
shout it and we'll repeat it.
Okay, so basically, if there is a project and it has like 1,000 or more C++ files, so do you really need to scan all the files to determine which ones are module interface units to know which one to compile first?
So,
repeat the question?
yeah, so the question is, if we have a project that has like hundreds or possibly thousands of CPP files, do we have to scan them all in order to figure out the module dependencies? And the answer to that is no, if the build system knows beforehand what your module interfaces are. We had this experiment with MS Build where we just need to scan the module interfaces, and it turns out that if you only scan those, that gives you enough dependency information for the rest of the program, because those are the only cases where you'll actually need to bottleneck the build system in order to build some kind of graph. Otherwise, all of the other translation units can be built in parallel because they don't provide module interfaces themselves.
Yeah, so in addition to that, even if you didn't give some hint to the build system, oh, this is my interface file and this is something else, the scanning, let's say you're going to scan the 10,000 files of project in there. So the scanning process is so fast because the specification of modules have been done so that you don't actually need to do full pre-processing. You only have to go through the file. So the preprocessor is line oriented. So you just have to go through the line of source code and look at a few couple of first words. Is it hash? Yeah, okay, you have to do something like we used to do before. Is it modules? Yes, okay, you just have to consider that line. Or is it import? Yes. Anything else doesn't count. Anything else doesn't provide any dependency information. So the scanning process is very fast.
Great. If I want to follow up on that, so basically, if I were to do a main file that would use, for instance, the MSVC compiler to basically support modules, so you need to provide, under my impression, some tool, right, or the compiler with some plans to actually do this scan of the first file, or X amount of lines. Do you provide some tool like that? Do you have plans?
So the question is, if you have a build system like Make, and you need to have this scanning, is there a tool that actually provides that information? For example, with MSVC. The answer is yes in the case of MSVC. Cameron here is the one who actually added that extension to cl.exe. You should just say cl/source dependencies, and if you want some more fancy information, you provide an option, and then the compiler will run, so the driver will run, and it will write in either on the standard output or in the file the dependencies in the format that I talked about earlier, that was pushed forward by the KitWar people. And that is what is being used today, for example, by the MS build system. But you can imagine that Makefile can be used to do that, and CMake, the feature that drive, let's say, Ninja or some other backend. Who else? Is it there?
Yeah.
Yeah, I actually have two questions. One is more of a Microsoft specific. The STD, the import STD, is that already implemented in Visual Studios, or is that a different feature? And the second question is, can you actually use the modules TS to kind of traverse your graph or to see, or your program to see where you're supposed to be handling exception specification through like the different functions?
Yeah, so the first question is whether the import stud is something that is only MSVC specific and implemented.
Or is it currently implemented?
Is it currently implemented? So since 2015, the MSVC toolset has been experimenting with some notion of stud module that it can use. And it is experimental, and it will evolve based on what WG21 is doing. So what is currently available in the MSVC toolset is very different from what is being proposed. And once it goes through WG21, the MSVC toolset will be updated to reflect that. And the second question is whether you could use the IFC format to go through your function bodies and see where an exception is thrown, or
Yeah, see where an exception is thrown, and if you're actually if you have any sort of try-catch to.
yeah. So whether a function there's some exception handling. I'll say more about that tomorrow. But the basic answer is yes. But I will say more about that tomorrow. I think we have time to have one
Sean?
more question.
How is the front end informing the linker about declarations of module ownership? You said that the front end's not doing the name mangling of module ownership, but my understanding is that at least L targets are doing the name mangling on the front end using
So to repeat the question, how is the front end conveying this ownership information all the way to the linker? Basically, what the MSVC toolset does is we have a communication channel to the back end, which is our IL that's generated from the front end. And this IL was modified to add some ownership information about the module. So if I say void F under the module purview, the compiler front end will say, okay, when I give the back end this F, and of course it'll hand it its mangled name, it'll give the ownership information to the IL for the back end. And what the back end will do is record that information in the COF sections for the linker itself. So if you are familiar with our object format, there's these COF sections which are specifically talking about like what is the linkage of a specific function or some kind of symbol that's embedded in the OBJ. And it's in that section that we record what module it was from and whether or not it's internal linkage, like module linkage basically, or external linkage, and should be treated with the strong ownership model. So it's all embedded in the OBJ file itself.
Yeah. So complementing what Cameron just said, no, he's right. The MSVC compiler, the way it is structured is that you have a front end that runs and generates some kind of intermediate format called CIL. But if you're familiar with Clang, for example, you know that Clang runs and then generates some LLVM bit codes, and that LLVM runs and then there's optimizations on it. So have that kind of separation. And if you work on GCC, I used to work on GCC a long time ago. So GCC doesn't use an intermediate file, but it has an in-memory representation where you have Gimple that is handed over to the middle end, and the middle end there's optimization, and then it writes RTL, which is that kind of immediate thing that you write back and generate code from. So what is done in MSVC compiler can be replicated for compilers that use the F format, for example. It's a GCC or Clang. So the idea is that instead of using name mangling to convey this information, so name mangling is a wonderful hack. Bjarne, apologies for saying hack, but I believe it was so it was this hack that Bjarne invented in the early 80s because he couldn't do anything with the linkers at the time. But we have been at a era, like long before modules, where we are doing a lot more than C used to do. So the linkers have actually been doing a lot more than what Yanning had to face with. So you can actually encode in the format that you're giving to the linker, the L format or the LLVM bit code that, hey, this function, this symbol actually happens to have these additional properties. And then the linker, when it's trying to link, will consult that information. So that technique could be used, let's say, for conveying exception specifications, this kind of stuff. Now, the linker at the end can add additional decoration, right? Like I was indicating earlier. But based on that information that the front end has conveyed to the backend, and all the compilers that I know of can do this. I've worked with 4 different compilers: GCC, EDG, and MSGC, and Clang. And I know with confidence that it can be done. The real question is whether there is a will to do it. I think there is a will if we put enough pressure that it is needed.
We're well out of time, so
Okay.
unfortunately, no more questions.
Thank you very much.
Thank you.